Today we're going to be working with one-point perspective. One-point perspective is a mathematical system for representing three-dimensional objects in space on a two-dimensional surface. So what that means is you're taking a flat sheet of paper or canvas or whatever it is that you're working on, and you're making the objects on it look like they're three-dimensional through use of lines and angles. We've talked about shading to make things look three-dimensional, but this creates a greater sense of depth in regards to having a foreground, a middle ground, and a background. So some things are closer to the viewer in the foreground, some things are a little farther away in the middle ground, and some are farthest away in the background. So when you have one-point perspective, this is a great example of it because this has train tracks, which we know are parallel. They never meet. If they did, the train would crash, and that would be bad. So in this image, it does look like they go back into space and eventually converge, and that is because of the one-point perspective. One-point perspective works best when you're standing in a direction where you can only look one way or the other, because there's also two-point perspective and other methods for drawing to create the illusion of depth as well. But in Art 1, we stick with one-point perspective. So to draw using one-point perspective, the first thing we need is a horizon line. And that is the line where the earth and sky appear to meet. So below this line, we have, it looks like a river that maybe the train tracks are going over. Above this line, we have the sky. So that's where the earth and the sky appear to meet. It is the horizon. We have a vanishing point. The vanishing point tells us which direction we are looking in. So the horizon line is used to tell us whether we're looking down at something or up above at something. A high horizon line would mean that you're looking at something that's more on the ground below it, whereas a low horizon line would mean that you're looking at something that's above that in the sky. The vanishing point tells us where we're looking. In this situation, we're looking right in the middle, but maybe your vanishing point could be off to the left, meaning that you're standing in the middle looking towards the left direction. Or your vanishing point could be towards the right. Just depends on which direction you're looking. So again, this is perspective, meaning where you're seeing things from. So we have our horizon line, and on our horizon line we have one vanishing point, hence the name one-point perspective. All of the objects in our picture are connected to the vanishing point by these lines called orthogonal lines. So the top of the train track bridge and the tracks themselves all connect back to that vanishing point. Those are called orthogonal lines. In this case, these are real-life things. So the lines represent the actual tracks or the trestles that hold the bridge together. But if we were drawing something more simplistic, like a box, a cube that's going back into space, those lines would represent the edges of that box that show where the depth is. Let's look at another example really quick. This one's a little simpler, so it might be a little easier to understand. Again, we have our horizon line. Notice in this one it kind of comes a little above halfway, so we're seeing more of the ground in this picture than we are of the sky. On the horizon line, there isn't a mark that shows where our vanishing point is, but because our road continues back all the way into the distance, we can see that our vanishing point is right in the middle of our horizon line. All of the lines on our road meet back at that point. In addition to the lines on the road, the edges of our tractor trailer and of our building over here all meet back to that point. So we started off with just this rectangular shape, connected the corners of that rectangular shape with orthogonal lines going to the vanishing point, and then we would use cut lines, and I'll show you what those mean in a moment, to show where the depth of our object ends. One-point perspective was considered to be rediscovered by a guy named Filippo Brunelleschi during the Renaissance, which was during the 14th through 16th centuries in Europe, where there was a revival of intellectual and artistic achievement and vigor. And so it had been used previously by ancient Romans and Greeks, but no one took the time to actually figure out how or why it worked and to do the math to prove that it worked until Brunelleschi came along. So we have a handful of different exercises that we're going to do to practice doing one-point perspective, and I'm going to show you an example as quickly as I can so that you have an idea of how to get started on your own. Using some simple shapes, it says select a vanishing point if one is not already provided, which it's not in this picture, and use a ruler to create orthogonal lines that connect the corners and edges that would be visible to the vanishing point. Add cut lines, and again we'll talk more about what that means, that match the original shapes of the object and indicate the depth of the object. Erase the remaining orthogonal lines after the cut lines and use graphite to shade the objects based on your light source to add the illusion of dimension. So I'm going to pick a vanishing point right smack dab in the middle. You don't physically have to have a horizon line. Again, it's just a line that represents where the earth and the sky appear to meet. If you're doing an abstract picture, though, you wouldn't have an earth and a sky. It's just an idea of how much you're going to see. So if my horizon line or my vanishing point is on my invisible horizon line, and this box comes below that, then I know I won't see the bottom of this shape because it comes below the vanishing point. Whereas these two boxes come below the vanishing point, so we're going to see the tops of those because of the perspective or the angle that we're looking at. So if this is my vanishing point, VP for vanishing point, then I'm going to use my ruler and connect all the corners of my shapes to the vanishing point using orthogonal lines. Now there is a little bit of a trick to this because I just said using all the corners, but unless our shape is transparent or translucent, we wouldn't see all of the corners. For instance, this one here, unless our shape is see-through, we're not going to see that line going back to the vanishing point because it's on the opposite side of the angle that we're looking at. So if this were a three-dimensional box sitting on the ground, you can't see this line connecting back to the vanishing point because it's behind the front panel of the box. But we can see this one on the left top that shows where the top edge ends. We can see the top right. And we can see the side of the box because our vanishing point is a little to the right of it, meaning that we're looking at the box from the right. So those are our orthogonal lines. Cut lines, again, show the depth of the object. So a cut line means you're showing where the object ends, how deep it goes. If this box was about as deep as it is wide, can kind of guess, we're going to add cut lines that mimic the shape of the box itself. So you always want to be parallel to the original object with your cut lines. So if this cut line is intended to look like the end of the top of the box, then I'm going to draw a line here. And like I said, I'm just kind of guessing at the depth. In real life, you might have an object in front of you and you could be exact, but we're just guessing for this. We're making it our own. So that line shows the end of the box top, and now we want a line that goes parallel to the side to show where the depth of the side of the box ends. So I'm going to meet that corner where I was just ending my first cut line, and I'm going to go parallel to the side line. Then I'd erase what's left of my orthogonal lines to make it look more realistic and clean. It says in the directions to choose a light source and shade your objects based on that light source. So if I put a little sunshine up here, then I know I'm going to have sun shining down on the top of my box and maybe a light value on the side where the sun might not get as much, or the object might not get as much exposure to the sun. This one is intended to look like it's open on the inside. So you want to think about which parts you would see. I'm not going to do it for you. I want you to kind of experiment with it. But we would see the outside of the box just like we saw this one, going towards that vanishing point with our orthogonal lines. But you would also see inside of this area of the box where this inner edge and the base of the inside are visible. See if you can do that one. Something important to talk about is when you have curves. And again, I'm just showing you really basic stuff for now. But if we had a curved shape, like a circle, then when you add your orthogonal lines, you don't have a corner to match them to. So what we want to do is use the outermost edges of our shape. So if you line your ruler up on your vanishing point and slide just the top section over, whichever's closest to your shape, until it's at the edge, and then use your lines to come down, your orthogonal lines. Do the exact same thing on the other side of this particular shape. Connect that outer edge to our vanishing point. So now it looks like we have a sphere that's either coming out at us or going back into space, depending on how you envision it. Our cut lines for circular objects, we just mimic the original shape. And then when we erase our orthogonal lines, it looks like there is a cylinder type shape that's coming out towards us. If we wanted to shade that to make it look dimensional, like the instructions say, then you might have some cross hatching or hatching going on over here to make it a light value, and then wrap around to show where the light source is shining from on this side. One thing to keep in mind is with complicated shapes like this guy, that you want the depth of your cut lines to be relative to the shape, same all the way around. So if my cut line inside of the shape was about this far from edge to edge, then I want my cut lines outside of the shape to be about the same. And again, I'm just sketching it in. I'm not actually using my ruler, which you will be doing. And I'm not connecting to the vanishing point, which you will be doing. But the way that I was able to make this one look three-dimensional is by making those cut lines appear the same depth all the way across. So if I add a little bit of shading, you can kind of envision that this is a square box with a square hole going through the middle of it. All right, you guys have 3 different worksheets. They progressively get a little more complicated on each one, and I want you to use those and see if you can figure out, using your rulers and putting in your vanishing points, how to make each of those shapes look like forms that are in real space.